Good afternoon, everyone. Welcome to the final presentation of Learn to Race. We are excited to have you here. I'm Satya, and this is Anirudh. This is Sri Kumar. And we also have our other trust members, Durvesh, Daniel, and Brandon sitting there. And first, I'll start with the agenda for today. We'll have a general introduction of Learn to Race for 10 minutes. And then each of the thrusts, they'll go over their experiments and their presentation. So we have 4 thrusts, so it's going to be a long presentation. Just letting you guys know. So starting with the introduction, what Learn to Race is about. Learn to Race is a capstone project for training an autonomous racing agent to navigate a racetrack in the Arrival Autonomous Racing Simulator. So it's using OpenAI Gym standards. It integrates sensor data, computer vision, and reinforcement learning to efficiently train and evaluate autonomous racing agents. This capstone builds upon the Learn to Race framework, which exposes a simulated racetrack environment as a gym interface, as well as Learn to Race benchmarks, which is a wrapper implementing standard RL paradigms rooted in the previous capstone projects. And the image here shows the overall working of the L2R framework and code. So as an initiative to democratize research in autonomous racing, Bosch Research proposes, advises, and collaborates with capstone projects in MCDS. And the major goals are to participate in real-world public autonomous racing competitions like RoboRace, enable scientific research in robotics and artificial intelligence, address the limitations of existing research simulators, develop safety-aware autonomous systems, facilitate outreach through public AI tasks and challenges, conferences, international workshops, and open source software contributions. We'll discuss about the timeline of how Learn to Race has evolved across the years. So in May 2022, CMU joins the RoboRace Autonomous Racing Championship, which is the first international championship for full-size real-world autonomous racing. And then RoboRace begins the 3rd season of autonomous racing called Season Beta in July 2020, where CMU had a podium finish at the Thruxton circuit conducted in the United Kingdom. And then we have the introduction of the Arrival Simulator and the Learn to Race task in July 2021. We'll talk about the Learn to Race tasks in further slides as well. The Arrival Simulator public release was done in July 2021. And then the Learn to Race Autonomous Challenge was launched in December 2021 with workshops conducted at IJCIA and ICML. And then in May 2022, we had the task 2.0 introduced with the results of the challenges and with refined metrics part of it. Coming to the iterations of Learn to Race, the major one in 2021 was introducing the Learn to Race framework, where the baselines were released and the Arrival Simulator was introduced. The framework conforms to OpenAI Gym standards, allowing versatile training setups, providing full control over the vehicle sensors and environment settings. And then in 2022, we have the Learn to Race Task 2.0 introduced. This contains the results for the challenge launched in 2021. And this iteration had refined metrics and focus on maximizing performance and safety in autonomous driving with new task definitions. The link for the respective papers, we have put it in the slides for people who want to read more about it. So coming to the motivations, safe learning requires motivation in general because autonomous systems, if deployed in the wild, are naturally unsafe. So we have to learn policies that are both safe and perform. Now the question is, as safety and performance do not usually go hand in hand, how to develop algorithms that have to maximize both. So we need challenging environments with that are proving grounds, and we have to envision autonomous racing to serve as a particularly challenging arena for developing safe and performant autonomous systems. And agents must drive at their physical limits where the slightest infraction could result in catastrophe. And we also need better methodology. We need to develop methodology that has safety awareness and robustness. Now, coming to the Arrival Simulator, which is another crucial component in the Learn to Race framework, which I think I've spoken a lot about till now. So we will see what it is. It's built on Unreal Engine 4, equipped with various sensor models. It helps transitioning from simulations to real-world implementations from the RoboRace series. More details can be found in the link that I've put here. And we also have an image of the racetrack, and the inputs will be obtained from these for our models and agents. So why is this a particularly challenging task? First point is we need to make sub-second safety critical decisions in a complex, fast-changing environment. And second, Both perception and control must be robust to distribution shifts, road features, and unseen obstacles. And third, we need to evaluate the joint safety, performance, and generalization capabilities of RL agents on multimodal perception because we have computer vision thrusts with sensor data and etc. So we have looked at how Learn to Race has evolved across the years. Now let's look at what the previous capstone teams have done. So the 2021 team, they were involved in the Learn to Race task creation and the challenge launch and publication. And the team in 2022, they introduced modularity to code base, and they also made a standardized framework with implementation of existing models. And they also developed thrust-specific algorithms and analysis. And we, this year, we have 4 thrusts, each with their own set of improvements and research goals. We also have trying to make changes to the existing framework as much as possible. And with that, I'll again introduce the 4 thrusts we have. The perception thrust, which has me. I'm Satya. This is Anirudh and Srikumar. And then we have the distributed RL reinforcement learning, which is by Brandon, who's sitting there. And then we have robust temporal context-based learning thrust by Durvesh. And then we have the RVOS development by Daniel. This is the overall system view of the Learn to Race framework. You can see the racing simulator and the framework and the agent mentioned here. We have also highlighted the thrusts, the distributed stack development and perception thrust and the context-based thrust. We're actually extremely grateful for the modularized code and baseline models present in the existing L2R framework. This actually has been crucial for the progress that we have made this year. We are excited to share our results with you. With that thought, we'll jump into the thrust-specific presentation for the perception thrust, which Anirudh will start now.
Hello, everyone. I will take you through the vision and the other sections for the perception thrust. Starting off with the problem description. So what is our problem context? Effective navigation in complex race environments requires advanced vision models for quick and reliable feature detection, and high-speed decision-making abilities are required in autonomous agents. And so our limitation with our existing vision encoder is that it fails to effectively distinguish between different states and conditions of the track. And we will tell you how we've tested this in the upcoming slides. So our motivation towards our solution is that we look forward to having an encoder model that can provide more robust embeddings when compared to the existing encoder, especially with respect to different features of the track. So our proposed solution is to develop a system that can capture relevant information effectively from a given camera input and be robust to unseen tracks along with fast inference. And we explore our proposed solution across 2 directions, the first being vision encoder architectures and the second being inference latency. In the first direction, our aim is to identify effective model architectures for learning better representations. So we try models that are traditionally good at segmentation tasks, and that would be our pre-training objective. The existing encoder is a simple variational autoencoder, not specifically meant for semantic segmentation. So we want to try other models which are specific to this objective. In our second direction, we look at utilizing high-capacity models in a manner that minimizes the latency impact while enhances the predictive capabilities. So we have a performance latency trade-off, which comes into play when we have a larger capacity model. While they might do well in capturing road information, they have a higher inference time, and we'll need to find a workaround with this. So our hypothesis for our thrust is presented. Let me take you through each of these hypotheses. The first hypothesis is that integrating advanced semantic segmentation autoencoders, such as U-Net, will enhance the performance of our agent. The reasoning for this is that U-Net has this special ability to preserve spatial information using skip connections, and this would enhance our learned representations. We evaluate the improvement using some key performance metrics, such as distance and reward during training, as well as the average success rate during evaluation. We'll explain these metrics in the upcoming slides. Our second hypothesis is that we can leverage information learned by larger encoder models to improve the agent performance without significant latency trade-offs using knowledge distillation. Our reasoning behind this is that knowledge distillation enables utilizing the latency advantage of smaller models when compared with the ability of larger models to capture superior and fine-grained details. And so in addition to the key performance metrics as mentioned before, we have a few other metrics to test the validity of this hypothesis, such as dice loss. the model size, and inference latency. Coming to our last hypothesis, this relates to the hierarchical control models, where we employ a cascade of models running at different frequencies. And this would allow the usage of larger capacity models in the encoder without significant latency trade-offs. The reasoning behind this is that a large model can provide a plan to the agent at a low frequency, and the agent runs at a higher frequency. So this can lead to better performance without a compromise of latency. The evaluation metrics are similar to that in hypothesis 1. So the major features of our project are twofold. The first being better visual encoders. So we explore encoder models that capture more task-related information, and our task here is semantic segmentation. We also try knowledge distill models within better visual encoders. And the second major feature is control-based hierarchical models, where we have a separation of control based on the run frequency. So we try to operate costly operations in a low frequency and vice versa. Our plan for this semester is as follows. So the fall semester goals were mainly divided into 3 main subtasks. Firstly, exploring UNet as a better encoder, knowledge distillation on UNet, and finally, hierarchical control models. And we had 5 major subtasks that we had to do in this semester. The first being data collection and pre-processing. The second being updating the vision encoder by using the UNet model, as well as training it on the new data. The third being visualizing the embeddings between the older encoder and the newer ones to see if the improvement can be attributed to the quality of the encoder. Finally, we have applying knowledge distillation to UNet and implementing hierarchical control models to use larger capacity models. So this is our milestone plan, where you can see the major goals listed. Hierarchical control models was our stretch goal, and we were able to work on that. Moving on to the requirements of our project. The intended users are researchers and academics, as well as enterprises centered on autonomous vehicle technology. So our project has a direct impact by providing researchers with a dedicated platform for enhancing algorithmic and sensor systems, so they can precisely refine and improve their systems using the L2R's advanced capabilities. Simultaneously, businesses in the self-driving car sector can find value in our system by gaining insights without the need for costly real-world testing and using L2R as a proxy for deploying a car in the real world. This is the context diagram, where you can see that the 2 main entities are researchers and academics, and the arrival simulator is our data source and sink. So the arrival simulator is where the framework does its actions and gets feedback from the simulator. And the researchers can use the L2R framework to experiment with different encoders and configurations, get feedback through the visualization dashboard, and businesses can deploy RL agents and get insights from them. So we have 4 main system functionalities. The first one being encoding RGB images and sensory data from the vehicle to a fixed state size representation for our RL agent. The second is that the encoding should help the agent differentiate between different track conditions. So turns and road boundaries should be detected by the encoder. The module should be configurable to enable faster iterations, suiting a research environment. And finally, the system as a whole should allow real-time logging of metrics to assess the performance of Learn to Race over a long run. The 4 main non-functional requirements are listed on this slide, with the most important one being on top. Performance, obviously, since Learn to Race is learning to race, achieving low latency encoding and swift decision-making alongside high accuracy decisions and are requirements for Learn to Race to succeed. And obviously, building upon previous capstone's contributions, interoperability and modifiability are important non-functional requirements, where we want the vision encoder to be implementing consistent interfaces for seamless integration with other RL agents, as well as it should be easily modifiable. So if I want to change the channel depth of the existing encoder, it must be easy. And finally, the vision encoder should be generalizable. So there should be consistency in performance across diverse racetracks expected from both the agent as well as the encoder. In terms of resource requirements, we have data and hardware requirements. So the data set, as we mentioned before, is generated using the arrival simulator. And the tracks include Thruxton, Angelcy, and Vegas tracks. About 11,000 RGB images paired with the gold standard segmented images were collected from the arrival simulator for supervised learning. And our primary computing resource is the Phoebe cluster. So it has high performance GPUs, including the 2080 Ti. For benchmarking our baseline, we also made use of AWS EC2, G4D, and XLarge instances. To give you an idea about our data set, you can see that the RGB image is here. And this is the gold standard segmentation map that we collected. We pre-process this map into black and white because we're only interested in the road region. Moving on to the design.
Now we come to the design of our projects, and let's split this into two parts. We have our assumptions that we make and the constraints that we have to work around in our project. When it comes to assumptions, we want to make sure that the data is reliable, that every image that comes in from the simulator is of proper standard and it's not corrupted, and that there are no interruptions in the flow of images, that every observation comes without any network bottleneck or any sort of issue like that. And that the latency between the simulator and our code base, because this is the primary interaction, should be minimal, the latency in that. And that the session should conclude when the agent goes off track. This is important because that's what we use to backpropagate the rewards during training. Now, the constraints that we had to work around, inference latency is, as we mentioned earlier, is very important to make real-time decisions in an autonomous driving task such as this. And also, the training duration of our models in this case goes up to 4 or 5 days, which means this is something that we have to work around when we're parallelizing our tasks and planning things ahead. And moreover, we also have required significant GPU resources to train our models. Now we come back to the system architecture diagram that we showed earlier. Here we work on the vision encoder part in the perception module. Here you see observations going in, and then the state encodings coming out from the vision encoder. Now, the question you might have is like, what do these encodings look like? What do they mean? And how do we train this encoder to provide these representations to the RL agent? And so this is a deep dive view into that. This is the system architecture of our encoder, and this is how we train UNet. So the Arrival simulator provides the input image and other sensor data into the L2R framework, which provides the input image to the encoder. Now, how we train this is that we showed you the data set earlier that had the black and white segmented images for every RGB image. We try to reconstruct that black and white image as best we can using this encoder decoder, and that would be our training paradigm. Once that is done, the middle layer would have captured all the information that's required for road segmentation, and at runtime, the input image goes into the encoder, and we get a fixed state encoding back that we supply to the RL agent for that to make decisions. Now, how do we test this? How do we go about doing that? Now, for test design, again, we work on the abstraction of the RL agent. And so we assess metrics on both the RL agent and the encoder. For the agent, we use average evaluation success rate, which we will talk about in the next slide. The distance the agent covers before leaving the track, the reward that the RL agent receives, the speed of the agent. And on the encoder side, we use dice loss, which we will again talk about in the upcoming slides. The latency of the encoder, because as we mentioned earlier, it is an important measure for us, and the model size and number of parameters that the encoder has. Now let's talk about average evaluation success rate. What this means is that we divide a track into a fixed number of segments, 10 in our case, and we want to see the proportion of segments that the agent is able to cross successfully. Now, why is this a better metric than simply using distance? Because you might think that gives should be proportional, but that's because the track isn't uniform in its challenges. There might be some parts that have turns, some parts that have straights, and we want to have a more robust metric that says what parts of the track it would cover, and so on. So this would simply be the number of track segments it traversed divided by the total number of segments that we have. And our average evaluation just means that we evaluate this over a number of episodes and take that average. Coming to dice loss, this is an important metric for our UNet training. And what this does is simply it takes the overlap between what our predicted image was and what our ground truth was pixel-wise and gives us a loss, an intersection over a union. Now we've spoken about how we test our project, and now let's go into what the risks and challenges are in the semester and how we deal with them. So since I mentioned earlier that we operate on the abstraction of the RL agent, we need to ensure that there is a risk that the baseline RL agent does not converge. And how do we mitigate this? Is we go about either debugging and making that work. In our case, we moved over to a different RL agent that we will talk about later. And that becomes a stable testing bed for all of our experiments. And the large amount of training time for a RL agent is mitigated by parallelizing experiments along with our other work such as analysis and so on. And our low latency requirement is satisfied by us working with smaller capacity models and also moving on to the hierarchical control-based models that we speak about in the next slide, in the future. So these are the tools and dependencies that we use. Oh, okay. So we primarily use Python and PyTorch, OpenCV, and OpenAI Gym. We use 1B for our logging, AWS EC2 for baseline benchmarking, and then Docker and Kubernetes on the Phoebe cluster for our primary training and evaluation. Now moving on to the experiments and results.
So let me take you through the baseline that we have. The baseline that we use is L2R Safety Lab. So the primary objective here is to enhance safety in autonomous racing by employing safe reinforcement learning. So L2R Safety Lab consists of two policies which are independently in charge of safety and performance. So the safety controller intervenes when the current state action pair is deemed unsafe by the safety critic. So you can see that the safety critic here, QS, makes the decision whether the current state is safe or not. And if the current state is unsafe, then the safety controller takes charge. And so the safe actor gives us the next step. If the current state is safe, then there is a different actor for which is in charge of that. So this is the baseline results that we have. As we mentioned, we are using average eval success rate, distance, reward, and speed as some key performance metrics. On the x-axis, we have the number of episodes that were completed, and on the y-axis, the value of each metric. So on our best evaluation run, we noticed that the best evaluation success rate was 0.3, which means that 3 out of 10 segments were completed successfully during evaluation. And our average eval success rate in our best evaluation run was 0.06. So this was averaged over 10 evaluation episodes. A bit about the existing variational autoencoder. This is just a simple VAE used to encode images, as we mentioned before. This was the architecture that we used. As you can see, it's just using Conv, 2D, and ReLU layers. We now move on to our first strategy, integrating UNet. UNet is a convolutional neural network architecture that is specifically designed for semantic segmentation tasks, particularly in medical imaging. So you can see it has a unique U shape, which features a contracting path, which is the encoder, and an expanding path, which is the decoder. And these are connected by skip connections. These skip connections help the network retain finer details, enabling it to produce accurate and detailed segmentation masks. Following an extensive review of literature, we opted for UNet due to the following reasons. The first one is the tailored design. As I mentioned, it's built specifically for segmentation. It has skip connections for capturing both high-level and low-level features. It's very parameter efficient, so it's not a very large model, and it's also data-friendly. The important point here is that it consistently achieves state-of-the-art performance on multiple benchmarks. For our study, we considered 3 variants of UNet with channel depth 8, 2, and 1. So channel depth is basically the number of channels in a CNN. And you can see the size and the number of parameters for each of these variations. We trained these 3 variants of UNet on segmentation. And you can see that the final encoding size, that is the latent space embedding size, is mentioned in this column, as well as the dice loss. So UNet 8, obviously being a bigger model, performed the best with the lowest dice loss, followed by UNet 2 and UNet 1. And you can also see that UNet 8, since it's a bigger model, has higher inference latency when compared to 2 and 1. These are some outputs of the UNet. You can see that the quality of UNet 8, which is in this column, is better than 2 and 1. In terms of results, so we integrate these trained UNet models with our existing Learn to Race framework. And you can see that the line highlighted in red is our baseline. And we have other lines colored purple, blue, and green based on the configuration of UNet. You can see that UNet 1 performs the best. So let me just isolate that. In comparison with the baseline, you can see that unit 1 performs significantly better with respect to the baseline in terms of the average eval success rate, distance, as well as the reward. In terms of the best evaluation run, we saw that the best eval success rate for Learn to Race agent after integrating unit was 0.5, which means that it could cover half the track successfully during evaluation. And the average eval success rate also improved significantly, almost 3 times. This is a demo of our agent with unit integrated with it. Yeah, so you can see that this particular video we extracted from our best evaluation run, where it's able to navigate most of the turns and curves.
One thing we wanted to tell about is the selection of the model. We had multiple variants like unit 8, 2, and 1. And we chose to use unit 1, and that's where we showed our results. And the main reason is given first is the encoding size. We noticed that there's a trade-off between performance and embedding size, where the encoding size is inversely proportional to the performance of the agent. So the final encoding size using unit 1, it's 16. And with unit 2, it's 32, and unit 8 is 128. So we chose to, that's one of the major reasons we went with unit 1. And the other is inference. The number of parameters for unit 1 is less, as we already showed. And some observations that we made. First, the agent's performance, it seems to degrade with larger embedding size. So using smaller models allowed us to get like smaller sizes and faster inference, which showed better performance in the learn to L2R runs that like Anirudh showed. And there are also instances where the agent violently turns to the right on the track, but could not find violent left turns in analysis. And an ablation study on unit and the baseline VI. So the question we had is, how do we know about the quality of the representations learned by the encoder? So we decided to use PCA to visually summarize the data. Separation and clustering between the classes in PCA, they signify better representations. So this is one way to answer our question. So we split our data set into 3 classes: curve on left, center, and curve on right. And this is the example of those 3 classes. We subsample images from the test set and classify them into left, center, and right classes. And these are the PCA plots obtained. The one on the left is with the older VAE, the one on the right is with unit. And you can see the clustering is better with unit compared to the older VA. Coming to knowledge distillation, which is our second optimization goal for this semester. So knowledge distillation in machine learning involves a compact model, often referred to as the student, drawing insights from a more intricate model, referred to as teacher, by emulating its output probabilities, thereby enhancing the student model's capabilities. So in our scenario, we employ knowledge distillation to integrate more expansive models, thus elevating performance. And we also investigate the balance between performance and latency, especially when deploying resource-intensive models. This is the overall framework for knowledge distillation. As you can see, there's a teacher model, which is a sophisticated pre-trained model with high accuracy on tasks. It represents the gold standard of knowledge. And then we have the student model, a more compact model, and its goal is to absorb the core knowledge of the teacher without like the bulk of the training. And the student model's training is based on 2 components. First is on the ground truth, which is using traditional losses, comparing students' predictions with actual labels or ground truth. And then distillation loss like dice loss that measures how closely the students' outputs are aligned with the teacher's outputs. So by minimizing these losses, the student learns to emulate the teacher while staying true to the actual data. And these are the results we got after applying knowledge distillation on unit. The crucial parts here are the final encoding size and the dice loss. As you can see, unit 2 with 32 and dice loss of 0.16, and then unit 1 with 16 and 0.182. Here we have results for different variations of unit with different hyperparameters. And the major ones that we had were batch size and the number of epochs we trained for with learning rate and everything. And here we again choose to go with unit 1 because we want like a faster model with less parameters and also considering the embedding size. This is the output we obtained with the student models. Our teacher model is unit 8. Yeah. And the results on this slide indicate that the SafeSAC combined with the unit 1 student, which is shown in blue, outperforms the baseline by a significant margin, which is in red, and also the unit 1 teacher, which is shown in green. And the best eval success rate we got was 0.7. This is in comparison with 0.5 and 0.3 of the baseline and unit teacher. And then also average eval success rate of 0.192 in comparison with 0.18 and 0.06. Coming to error analysis for this, when you look at the unit 1, when there are like too many objects in the background, the curves, they introduce distortions. So we think we might require better image pre-processing and optimization techniques, and also maybe better teacher-student training objectives. Now, Srikumar will talk about the hierarchical-based approaches.
So far, what we've seen is that we had a model unit to segment the road boundary effectively. And to take care of the issue of latency, we had to constrain ourselves with a smaller model with fewer number of parameters. But why do we have to make this compromise? What if we don't have to do this? What if we can maintain the same level of latency, but still use a larger capacity model that can capture a lot more information? And that's where using hierarchical control-based approaches come in. So on the left, you can see the traditional way that we operated, where both the encoder and the low-level agent, the RL agent in our case, operate at a high frequency. So for every image that comes in, the RL agent does perform a particular action. Contrast that with what we propose is that we have an encoder or a planner that runs at a lower frequency, which means it takes in a bunch of images. It produces a plan for the low-level RL agent to work on, and that agent works at a higher frequency and dispatches actions using that plan. So here is the pseudocode for the same. The key point to note in the pseudocode is how we go about the planning phase. So we have a low-frequency planner frequency, which basically means that every n time steps, that's when we use our plan. And for the rest of the time steps, we basically work off of that plan and then allow the RL agent to use both the current observation and the plan to navigate its course. Now, we went through, this is to basically summarize all the literature that we went through in one slide. So our goals when we went to a literature review was see how do we go about planning? And one of the ways that a plan is represented in literature, a popular way is to just use XY waypoints as a means to tell the RL agent where to go. So that's our plan representation. But we also wanted to know what modalities do these works use and what information we need for planning. So in the modality side, we have the RGB camera, the depth camera, say the GPS or the current position of the vehicle, and the speed of the vehicle. Now, a tick there, the green tick means that we have access to that from our L2R framework in this current capstone. And the cross means that we don't have access to it. And when we come to the info used for planning, we do not have a top-down map of the environment, but at the same time, we have a bird's eye view that can be generated. And I'll talk more about why and how that works. So coming to a bird's eye view for a top-down map representation. Now, this is basically trying to get a top-down view generated from what we see around using the RGB cameras. And this can better help any agent navigate city streets or any real-world environment. But now we can ask ourselves the question, given our setting, do we really need a top-down map for our experiments? And the motivation for all this is primarily that we want to make as much progress in a brief time as possible. That's our goal here. So if you look at a top-down map, in this case, this is an image of a city street taken from the Cityscapes dataset. And this would be the top-down map on its right that you see, the one with the pink and the green cars. Now, given that in our setting, we don't have any obstacles, and we only have one path. We don't even have any intersections that we want to navigate to decide whether we go left or right. So given that, we figured that our UNet representation pretty much gives us a lot of the information that we already need. Now let's move on to how we predict waypoints given this information. We subsample 4 equidistant points, and we mark their center line. And we try to basically nudge the agent to go towards the center of the track. Now, a question we might ask is the center line always ideal? No, it is not always ideal, because for sure, if the vehicle is moving too fast, you do not want to stay on the center line. You probably want to go towards the edge of the track and then turn in. And another question, but another question is, why use the heuristic of the center line, and why not use deep learning models for this task, like an LSTM or any other model like that? Now, popular works do use transformer-based models and LSTM models, but in our case, we did not have the training data that was required to use an LSTM in our setting to adapt it to this application. Now, once we get the center line, we mark them as XY points. And how do we fit them into the encoding? That's shown in the bottom of the slide, where we basically concatenate all these XY points along with our speed and front camera encoding. And we also provide the time step of the current time step, so it knows which of those 4 points to sort of get to. Now, moving to the results for these waypoints, unfortunately, the results were not good, but our goal with this experiment was to try out different ways of encoding this previous part, like how we concatenate these vectors, and see if that has any impact on performance. So on the purple, you see with waypoints, which means that the XY points, but sans the time step. That does not have the time step. The yellow is with the time step, and the red is where we provide the only the current waypoint, which means at the first time step, we provide the lowest one. The next time, we only provide the second one, and so on. While most of them did not yield a good success rate or reward, one different thing that we saw was that when we used only the current waypoint, the average eval speed was higher than with the other 2 approaches, which match the traditional approach. So we wanted to know why this is the case, like what's really happening. And it turns out that the vehicle actually stays at the center of the track without veering off too much left or the right, but it comes to a complete stop. Because this is probably the case because in a way, the inductive bias of the model is to try to stay as much to the center of the track as possible. And how this works is that during training, it might see that the x-axis points are, if they're in either extreme, that the reward is low because it basically veers off of the track. So this way, it's possible that the agent found this as a stable state that says that, okay, I'm at the center of the track and this could be okay, and it say kind of stops. So, and but of course, we would have to analyze this more to find out why this is the case. And that is the work that we had done on our stretch goal. Now, to conclude, at the beginning of the semester, our initial objectives were to identify effective model architectures for learned representations to basically distill down what we see from the environment, and also leverage large capacity models in a way that does not affect latency. And to this end, when it comes to the first objective, our efforts on UNet has yielded a significant improvement in how we represent our observations. And to the second point, our work on hierarchical approaches, while did not yield results, serves as a starting point for further exploration that anyone can pick up on. And and moving on to potential future works, what can be done after this? We can definitely work on better ways of planning waypoints, as opposed to just taking the center line, using more ML-based approaches to optimize this path selection. The other can be attention and representation. What I mean by that is right now we provide a state encoding of fixed size, say 16, but what if the RL agent could attend to specific parts of that encoding and better correlate what's going on there? The third one is real-world generalization, because in the end, our overarching goal is to use this as a training and test ground, and our end goal is for these vehicles to be deployed in the real world and for it to work there. Finally, we want to make sure it can operate in dynamic environments like changing weather conditions and road surfaces and different multiple settings. And this is the end of our work. And now let's reflect on what the work we did in the past semester. So to start off, we can talk about what went well for us. Initially, in the initial parts of the semester, we had to debug the existing baseline setup that we had, the RL agent, and going through that exercise definitely taught us a lot about the container environment and what factors are involved. We were able to stick to our planned timelines and work on and this allowed us to work on our stretch goal as well. And we also found out that knowledge distillation retained the performance of the encoder successfully with a smaller model, and we were able to slightly increase performance. On the non-technical side, navigating the uncertainties with the baseline that we spoke earlier was something that helped more in terms of planning and then looking out for and making contingency plans, basically. And working on multiple goals simultaneously, splitting the work amongst the three of us effectively, something which went well. Now let's go on to what we could have done better. Definitely on the technical side, when we come to the hierarchical control-based models, we could have tried out more ML-based approaches. The reason that we were not able to do this is because given that it was a stretch goal, if we had visited the literature very early on in the semester, we could have, say, planned out to find out how we get this data and get the resources that we need for this particular exercise. That's something we could have done better. And again, experimenting with other state-of-the-art encoders is something we wish we could have achieved. And on the non-technical side, while because every training run takes about 4 to 5 days for us to run, it can have an impact on our schedule. While we did try to mitigate this as best as possible, we still feel that we could have optimized this a little more around the planning side about how we do our work alongside this training. The next point is planning for things to go wrong, again, revisiting the baseline issue, where if we had better planned for things to go wrong, maybe we could have made even faster progress in picking that correct RL agent and then moving forward from there. And yeah, the final point revisits what I spoke on the technical side, which is visiting our stretch goal early could have helped us get access to more resources. And that's the end of the presentation. We can use the appendix to answer any questions you may have.
Okay, great, thank you. Good job. Does it go back to the hypothesis slide in the beginning?
Yes. Yeah.
Right. So I guess what I wasn't clear about at the end was what the actual knowledge distillation result was. So it seemed like you picked the right UNet model, and that worked out okay. I think what was the actual knowledge distillation experimental condition? I guess I missed that.
So we used a larger UNet model, a UNet with channel depth 8 to act as the teacher, and we used two other UNet models, UNet 1 and 2 as our students.
Okay, and then you were able to just use those for the experiments. Great. Okay, thank you. It's been a long day, so I'm having trouble holding all of this in my head here. You guys did a great job presenting everything in a very clear and consistent way. Can you go to the pyramid with the non-functional requirements?
Yeah.
So I think here you certainly gave very detailed goals for the top two. And I think that it's fair to say that you did enough to actually show that those were maintained. But did you do anything to really test modifiability? I guess you tried some changes in channel depth and you were able to run the experiments there. Did you do anything on racetracks where you only trained on one and then tested on another?
No, we did not. So for our setting, we only used the Thruxton racetrack exclusively for the entire semester. That's what.
Okay. So that's an obvious thing that somebody could do. And a future step would be to take this and then try it out with the other two. Okay. So you did encounter some risks, and I guess what I was wondering about is how those influenced your decision-making and milestones. I mean, everybody shows a Gantt chart and says, here's our Gantt chart. But what actually changed for you guys? And in particular, I guess what I could say is, if you had known about those risks, or let's say you knew everything that you know today, and now you wind the clock back to January, what do you think you really would have done differently? The reflections you presented were really good, but they were kind of tallying everything up. And now I want you to tell me sort of like what you would have done differently.
I think on one perspective, initially we suspected a hardware issue, and that's where we ran circles around looking for, okay, what could be the hardware issue? And it took a lot of time, right? Okay. And which is why we did planned for that in the first month by sort of pushing our UNET forward, backward by some time, so give us a buffer time for us to work on this. But obviously, had we ruled out the hardware issue early on, we could have more immediately moved to the new RL agent that we use for the rest of the semester, and that would have saved us a couple of weeks.
I also got the impression that training time was like a big bottleneck for you guys. Can you suggest any way to reduce the training time? I mean, you were under the gun, so you didn't really have a lot of time to investigate like different ways of, refactoring the training and doing it differently.
Oh,
Do
so
you have any ideas about how you might reduce the training time?
that is actually one of the primary goals of the distributed RL trust. So that we distribute training and we try to reduce that, bring that down from 4 to 5 days to maybe 1 day, and that saves us all a bunch of time.
So Brandon's gonna come and save the day.
Hopefully. But
All right, thanks, guys. Great job.
thank you so much.